Welcome back students to our second lecture of this lecture series on chemical kinetics. In our lecture 1 we discussed about rate of a chemical reaction. We discussed about mathematical expression of a rate of a reaction. Now today in this lecture 2 we are going to talk about molecularity and the order of a chemical reaction. At the end of the lecture we are also going to learn about units of rate and rate constant of a reaction. Now these two concepts are crucial to understand the rest of the chapter. So I request students to pay close attention to understand the concept of molecularity and order of a reaction. So in our lecture 1 we learned how to express the rate of a reaction from a given chemical reaction, right? Yes, if the chemical reaction is N1A plus N2B, that means these are my reactants molecules and these are my products where C and D are products. Now when we write rate, the negative sign appears when in case of reactant, and a positive sign appears when we try to write the rate of a reaction in terms of product concentration change. Now the coefficient N1 comes as 1 by N1 in the rate equation and N2 comes as 1 by N2 in the rate equation. Similarly, for N3 and N4 it comes as 1 by N3 and 1 by N4 in the rate equation respectively. And after understanding this concept, let us solve a small question where the rate is given as minus half dp dt plus 1 by 5 dr dt and minus dq dt. Now let us look at very closely where these two signs are different, negative and positive. These negative signs clearly tells that P and Q are your reactants and R is the product. And the coefficient 1 by 2 here and 1 by 5 here clearly tells you that the coefficient of P in the rate reaction in the equation will be 2, and for R the coefficient is 1 by 5 here, so the coefficient of R will be 5 in the reaction, correct? But here the coefficient is 1, so it will be simply 1. So the complete reaction equation will be 2P plus Q equal to or arrow 5R. Okay, so let us move to the main concept slowly one by one, but before that we need to understand the elementary reaction and complex reaction. Even before that we need to understand the reaction coordinate first. So let us look at this reaction where R is my reactant and P is my product. Now this is the energy axis, that means the energy is increasing in this way. So R has energy this much, P has energy this much. Clearly P has lower energy than R. That means P is more stable than R. When a molecule has lower energy, that means it is more stable than the other one. Now every reaction consists of two things. One is uphill, this is like a hill, right? So this is the uphill process and this is the downhill process. Now at the top of the hill it is called transition state. Now the energy required to go from this point to the top of the hill is called the activation energy. Now you need to understand that each and every reaction has this kind of diagram where there is uphill processes and downhill processes. Now what is this coordinate, this x-axis? The reaction coordinate. Okay, let us look at this reaction coordinate closely. For that, let us consider this reaction where H2 plus Cl2 is giving rise to 2 HCl molecule. What happens during the reaction? This is your H2 molecule which has this bond. Now during the progress of the reaction, this bond becomes weaker and the bond distance increases. So the bond length increases with the progress of the reaction. So the parameter, it is one of the parameter that gets changed during the reaction or during the progress of the reaction. So reaction coordinate can be several things like bond length here. So it can be bond angle as well. If the bond angle gets changed during the progress of the reaction, it could also be dihedral angle. Now Simply, if we try to give a definition, the reaction coordinate is a parameter which dictates the progress of the reaction. Okay. So after understanding the reaction coordinate, it will be easier to understand the concept of elementary reaction and complex reaction. Now this is the case where we will try to make you understand that what is elementary reaction. So these reactions are also called single step reactions or simple reactions. Now let us consider that R is going to P. This R is my reactant and P is my product. Now this is the same process, same picture as I have shown before, and as you can see that here is only one transition state. So for elementary reaction, the number of transition state is only one. There is one uphill process and one downhill process. Alright. Now if this reaction is an elementary reaction, that means if you mix A and B after effective collision, it gives rise to product AB. What does it mean, the effective collision? It means that B has to come to the correct point and collide with A. Similarly, if this reaction is an elementary reaction, so B has to be on the right position and collide with A and C simultaneously to give rise to the product ABC. So these collisions are called effective collisions. Without effective collisions, the product cannot be formed. Now when we increase the number of molecules from 3, that means here A plus B plus C plus D, 4 molecules are involved, the effective collisions becomes very hard, and these kind of reactions cannot be elementary reaction. Okay, so for more than 3 molecules, when the more than 3 molecules are involved, the elementary reaction is not possible. Now what is complex reaction? As we have seen that for elementary reaction there is only one transition state, but for complex reaction there is one intermediate state, and the number of transition state is not one. As you can see here, the R is going uphill process and it reaches the transition state 1, and then it reaches to another stable state which is intermediate state, and then again it rises and it reaches the transition state 2. So there are 2 transition states, and then it gives rise to the product P. So there are also 2 activation energy barrier. So as you can see, E1A and E12 are the 2 activation energy barriers. Now complex reactions are of several types: consecutive reactions, parallel reactions, and opposing reactions, where in case of consecutive reactions, A is giving rise to B and then B is giving rise to the product C. For parallel reaction, A is your starting material, and from A you get simultaneously B and C together. For opposing reaction, A is giving rise to B, and again the B is again coming back to the form A. So this is called opposing reaction. So okay, we will talk about these 3 reactions in detail in our advanced classes. So let us move to the concept of molecularity. Now molecularity is the number of molecules participate in the rate determining step of a reaction. Now what we know, for elementary reaction there is only one step, so that step has to be the rate determining step. Now for elementary reaction it is very simple to define the molecularity of a reaction. Now for elementary reaction, let us consider A is giving rise to P, where A is your reactant and P is your product. Clearly you can see that one molecule is involved in this reaction, so the molecularity of this reaction is 1, and that is why we call it unimolecular reaction. Whereas in this case 2 molecules are involved, or 2 molecules participate in the reaction or in the rate determining step. That is why this reaction has a molecularity 2, and that is why we call it as a bimolecular reaction. Similarly here 3 molecules are involved and we call it as termolecular reaction because the molecularity becomes 3. However, the case is quite difficult for complex reaction because the definition says the molecularity is the number of molecules participate in the rate determining step of a reaction. Now let us consider this complex reaction where A is giving rise to B and the B is again giving rise to C. Now there are two steps from A to B, step 1, and B to C is the step 2. Now you need to find out which step is the rate determining step. Then only we will be able to find out the number of molecules that participate in that step. Now to find out the rate determining step, you need to find out what is the slowest step, because the slowest step is the rate determining step. This is very important point. You need to remember that slowest step is the rate determining step for any complex reaction. So as for example, how do you find that? You need to do some experiments to find out which one is the slowest step or which one is the rate determining step. Now if I tell you that your step 1 is the rate determining step, that means only a molecule participate in the rate determining step. That means that your molecularity of this reaction will be 1. Now what is the order of a reaction? Okay, so as we understand the elementary, as we understand the concept of molecularity, and we can talk about molecularity from a reaction scheme, right? But in case of to determine the order of a reaction, we cannot do that, because order of a reaction can only be obtained from the experimentally observed rate equation. So you need to find out the rate equation first. But it is quite similar or easy for elementary reaction. Okay, let us look at this. Now as in our lecture 1 we also talked about this, Peter Weig and Goldberg introduced the concept of law of mass action, where this law says that the rate of an elementary reaction is proportional to the product of the concentrations of the participating molecules. Alright, now let us look at this reaction where A plus B is giving rise to P product. Now what this law says, the rate of an elementary reaction, if this is an elementary reaction, the molecularity would be 2, because only 2 molecules participate here in this reaction. Now the rate can be proportional to, because it says that the rate of an elementary reaction is proportional to the product of the concentration. The product of the concentration A multiplied by B, okay, because A and B are the participating molecules. Now what we have learned from our lecture 1, that rate we can write as minus dA dt or equal to minus dB dt if we try to write this rate in terms of reactant concentration change with time. Now from this we get that rate is proportional to concentration multiplication A multiplied by B, and so we can put a constant K to remove this proportionality sign, and we can put a equal sign. So rate is equal to K, where K is the proportionality constant and we call it rate constant, into A into B concentration. Now what is the order of the reaction? Now you have already found out the rate equation for elementary reaction. Now order of the reaction is the sum of the power of the concentration. Now what power of the concentration is 1 here and power of the concentration is 1 here. So power of A concentration, power of B concentration is 1 plus 1 is equal to 2. So the order of the reaction is equal to 2. Now interestingly, the molecularity of this reaction is also 2. So the important point here is for elementary reaction, the molecularity and the order are equal. But for complex reaction, this is again very difficult to say, because for that you need to find out which one is the slowest step or which one is the rate determining step. After finding out the rate determining step, you need to find out the rate equation. The rate equation is not simple here. You will find out that rate depends on the concentration of A and concentration of B, but the powers are not goes with the coefficient. It is completely experimental numbers, where that is why I put alpha and beta here, and the order of the reaction will be again the sum of the power of the concentration, where power of A plus power of B, and the order of the reaction will be alpha plus beta. Now if I ask you that what is the order of the reaction in terms of concentration A only with respect to concentration A, so that would be only alpha. and what is this order, this alpha plus beta order is the overall order of the reaction. And again, if I ask you that what is the order of the reaction with respect to concentration of B, the answer would be only beta. So for elementary reaction, as we know that molecularity and order are same number, so for unimolecular reaction the order is 1 and we call it first order reaction. For bimolecular reaction the order is 2 and we call it second order reaction. Termolecular reaction the order is 3 and we call it as third order reaction. But for complex reaction the rate can be different, and rate can be completely, rate is experimental factor. And if I consider that this is my rate determining step and the rate is found out that K A to the power 0 and B to the power 1, the overall order of the reaction will be 0 plus 1, which is 1, and order with respect to A will be 0 because the power of A is 0, and order with respect to B will be 1 because the power of B is 1. Now similarly here the rate is equal to this, we found out this equation from experiments, and overall order is 1 plus 1 2, order with respect to A is 1 and order with respect to B is also 1, as the power of B is 1 here. And again similarly rate is if rate is found out that K A square B1 and overall order will be 3 because 2 plus 1 equal to 3, order with respect to A will be 2 and the order with respect to B will be 1. Okay, so after understanding the concepts of molecularity and order, let us look at the crucial differences between them. The molecularity of a reaction can be calculated from a reaction scheme, as we have seen before. No experiments are needed for this, but for order of a reaction cannot be calculated from a reaction scheme. It is always an experimental rate equation. You need to find out the rate equation by experiments, and then only you will be able to comment on order of a reaction. Now molecularity cannot be a fraction because as we see it says the number of molecules. So number of molecules cannot be a fraction. You don't say that 1.5 molecules of oxygen and the order of the reaction can be fraction, because this is an experimental factor. We can sometimes we found out that order of a reaction can be fraction. Now molecularity of a reaction can never be 0, because if there are no molecules to participate in the reaction, then there is no reaction, right? So molecularity cannot be 0, but order of a reaction can be 0. This is very interesting, and we will talk in detail in our next lecture with various examples, and we will also try to solve the rate equation, integrated rate equation for 0 order reaction. Now the second part of this lecture, where we will try to learn about the units. Let us consider a first order reaction. So A is going to be product is B and A is my reactant. So as this is a first order reaction, I already said that rate will be K A to the power 1, because this 1 will dictate that this is a first order reaction. Now what is the unit of concentration? We call it molar, right? So molar is mole per liter. Now what is rate? Rate is the concentration change by time change. That means the unit of concentration by unit of time. So what is the unit of concentration? Unit of concentration is mole per liter and unit of time is second. So what is the unit of rate? The unit of rate becomes mole liter inverse second inverse, right? Now we also know that rate is Ka, where K is the rate constant. Now what is the rate constant? Then rate constant becomes, unit of rate constant is equal to the unit of rate by the unit of concentration, right? So unit of rate, we already found out that mole liter inverse second inverse, and the unit of concentration is mole liter inverse. So this mole liter inverse gets cancelled out and we get only second inverse. So for first order reaction, the unit of a rate constant is second inverse. However, for nth order reaction, this case is very generalized, and where you can see that if my rate is Ka to the power n, this n dictates that this is a nth order reaction, and this n value can be from 0 to any value like infinite. Okay, so but in general we found out that this n can be 0, 1, 2, 3, 4 or etc. Now unit of concentration is, again we know that mole liter inverse, and unit of rate is mole liter inverse second inverse. So in this case the important thing is that when you find out that unit of rate constant k is unit of rate by unit of concentration to the power n, so that means here the mole liter inverse you will find a n value here. Now if you calculate, now mole to the power n and liter to the power minus n, and then if you try to common out that mole, it becomes mole liter inverse whole to the power 1 minus n second inverse. Now if you put n equal to 1, that is for first order reaction, it becomes mole liter inverse to the power 0. Now any value to the power 0 is 1, so that becomes you will get only second inverse, that we have seen in our last example for first order reaction. So it clearly matches with the expectation, right? So this is the point you need to remember, that for any order reaction, for nth order reaction, the unit of rate constant will be mole liter inverse whole to the power 1 minus n second inverse. Now after learning these things, let us solve two questions with solutions, where the question is from JEE Advanced 2014 and it is directly on order of a reaction. Now this is an elementary reaction M to N. The rate of disappearance of M increases by a factor of 8 upon doubling the concentration of M. What is the order of a reaction with respect to M? Now the solution is here, where the rate of disappearance of M is minus dm dt. So rate can be expressed as k m concentration to the power n, because n is the order and we don't know that what is the order at this point. So we need to find out what is the order of the M, the order of the reaction with respect to M. Now that given that when the rate of disappearance of M becomes 8 times means it was R, but now it becomes 8R, then you need to double the concentration of M. That means you had M here, but now you need to put 2M instead of M in the rate equation. So if we try to form two rate equations, where we get R equal to k m to the power n, and now the second equation becomes 8R equal to k is the rate constant, and here instead of m you need to put 2m, and the order of the reaction becomes same. Now dividing 2 by 1, what we get that n value is equal to 3. So the rate of the reaction, the order of the reaction with respect to m is 3. So option B is your correct answer. Now let us move to the second second problem, where higher order reaction greater than 3 reactions are rare. I discussed this in our lecture, and this question is from JEE Main 2015. Now what happens when you increase the number of molecules or higher order? When let us talk about this, 4 molecules are involved. So what happens? You need to have the effective collision, right? So 4 molecules effective collisions are very difficult. As you can see, 4 molecules are colliding, but B and D are not touching each other, right? So there is no effective collision between B and D. So if I try to draw this, what I need to do, so there has to be a simultaneous collision between these molecules A, B, C and D, which is very difficult here because of steric congestion. Okay, so the answer is low probability of simultaneous collision of the reacting species. So the option C is your correct answer. Okay, so this is the assignment. Please solve the assignment and comment below your answers. So okay, so in this lecture what we discussed about reaction coordinate diagram. We also discussed about elementary and complex reaction. We talked about molecularity, rate constant, order of a reaction, and also the units of rate and rate constant for first and nth order reaction. From this nth order reaction you can find out the rate constant and units of rate for zero order reaction, for second order, first order, third order, fourth order, or any order reaction you want to find out. Okay, so we also solved two problems and find out their solution. Now we also gave one assignment. I need students to solve the assignment and comment down your answers. That's all. If you like this lecture, please like and share with your friends, and please subscribe if you have not subscribed us yet, and hit the bell icon so that you don't miss a single video from our channel. Thank you.